wait until the talk is over for applause. All right, welcome to this talk on data storage in entity component system, which sounds like a very confusing title. I'm not entirely sure what this talk is about. So hopefully you will help me figure it out for when I actually do it in the future, because I'm not entirely sure. I'll explain the story as I go. So if you've ever been like to or watched like a presentation from a game industry talk, like for example GDC, I think is the poster child of this. You will have a guy who go on stage and he's going to talk about a technical topic for about 30 minutes to an hour. And then the first question, like I almost have a bingo card for this, he will go and say, by the way, regardless of the topic, have you tried using ECS? That would solve all your problems. And I'm like, okay, so I tried, right? Maybe it will solve all my problems. What do I know? I tried to look at Google a bit. Why is the train going so hard? Where's it coming from? I have a cursor that needs to die. There we go. It's not a great graph, but it does show that a big spike somewhere in 2018. Which is tied to Unity announcing that they were making like a super cool like demo with ECS. But more importantly, apparently Sweden is the place that searched for ECS the most, followed by South Korea and China. Don't ask me how, but Google says that Sweden is the ECS country, so I guess I'm at home in the right place about this. So hi, I'm Mathieu, or Mathieu, depending on your accent. I'm a tech lead at Paradox, where I make Arcs of Iron and other stuff. Speaking of Arts of Iron, we very recently released our latest DLC, Arms Against Tyranny, and I just said that this is maybe the one time I can see my game on top of Baldur's Gate in the sale. That is not gonna last, but let me enjoy it while it lasts. We will even have good reviews, which is very rare because our fans are like rabid usually in the reviews. That's the good news. The bad news is it shipped Tuesday. Then I had to patch it yesterday. Then I had to patch it today. So, well, let's just say this talk is very work in progress because I was hurt by other deadlines. So, like I said, I'm not exactly sure what this talk is about. Hopefully, we'll figure it out together, and you will tell me. Especially, don't hesitate to tell me. I'll try to just poll around. Like, do you already know this topic? Should I just move on? Because somehow I made 100 slides anyway. So we're going to talk about ECS, obviously. What is ECS, or Entity Component System? Obviously, usually when you talk about ECS, you need to talk about data-oriented design and things that go with that. And cache-friendly data structure, and all those funny CPU things. So first, let's talk about hardware. Because at the end of the day, I know people love to talk about the C++ virtual machine, but turns out the C++ virtual machine does not exist. It's not real. It's not real, it's just some words on a paper. It doesn't exist. What exists is actually your actual CPUs, which runs your actual code in an actual machine. And it has a bunch of quirks that are very interesting, but technically not in the standard, because the standard is written against this magic abstract machine that does not exist and have no software or hardware problems. Well, software maybe, but not hardware. And turns out, as Joel Spolsky said, like, 15 years ago, 20 years ago, all abstractions by nature are leaky, and this is probably one of the biggest one in my view. It's the one that taught you that all CPUs are magic. So, I mean, CPUs are magic. I think we can take a minute, and I think the previous talk helps a lot to appreciate what CPU founders, manufacturers, and everything can do for us. Because, you know, your modern CPU is like what? Well, not this one, but actual modern CPU is like what? Like 4 gigahertz, 5 gigahertz in turbo mode? That's 4 to 5 billion cycles per second, if my math is correct. And most arithmetic operations on a CPU is like a cycle or two. Like you do an addition, you do a copy. You can do 5 billion additions easily in 1 second, and that's if you're not trying, which is kind of amazing. And even if you try to go for like scary stuff that they told you in school that you shouldn't use, like division and square root, you can do a square root on a modern CPU in like 20 cycles. Divide by how many, like you can make millions of square root a second. That's not, that your CPU is just gonna laugh at you. It's fine. And if you start doing SIMD and other intrinsic funny things, you can even do better. Like you can do 8 additions per cycle somehow. It's pretty magical, and it's pretty cool. But as we saw in the previous talk, which was a great introduction to my talk, I guess, CPUs can only operate on data that is physically collocated. That sounds very complex, but what I mean is that there's this thing called physics that I'm really bad at. But from what I understand, there's concepts like the speed of light, current, and stuff like that, which means that data that is like physically on the chip you can access fast, like use your 5 gigahertz of speed, but your RAM stick that is, further away and there's a memory bus in between you and them, not so good. So basically, if anything is in a register, those small like memory cells that your CPU has to just store temporary data, or in L1 cache, we'll talk about caches, don't worry about it, you're good. But else you need to load it. And that's where it starts being a problem, right? So, well, we all know that, right? You have your nice CPU and your nice RAM, and they just have a bus in between them and they talk together. And according to like most findings that I've found, and apparently it hasn't moved a lot since the last 10 years, it's about 100 nanoseconds to fetch some data from your memory stick if it's not on the chip. Which, I mean, 100 nanoseconds, I don't think I can even wrap my head around that, because that's just a number. It's so tiny, it's really hard for me to compute. But maybe we can compare it instead and realize that, if it's in the L2 cache instead, it's like about 4 nanoseconds. And if it's in the L1 cache, it's about half a nanosecond. And, well, if it's in a register, it's basically free. Like, it's part of your addition move cycle. It's magic. So if we try to normalize this and put it on a 1 scale, assuming that the L1 cache is like the 1, it's 200 times slower to access the memory stick, and 8 times slower to access L2 cache, which again are big numbers. Maybe, I don't know, programmers are usually good at numbers above like 2, and then it starts getting difficult. So I'm gonna help you a bit with this, all right? So I tried something with PowerPoint that I saw in another talk that I found very funny, and I tried to recreate. So I'm gonna try to scale to show you how fast it goes to fetch, all right? So we're gonna fetch from L1 cache. There we go, we're done. Okay, same operation from L2 cache. Sorry, there we go. Not too bad, right? All right, let's fetch from memory. Wait. About 50% there. Wait a minute, we're almost, we're getting there, the data is almost here. Wait. Come on. There we go, we got our data. Right. So I like showing that to junior people when they say, I don't think it's that important that the memory is. It is. It really is. Like, it's orders of magnitude slower than doing basic arithmetic to fetch some data. Like, adding two numbers is basically wait 5 hours, then spend 1 second adding them together, and then wait another 2 hours to write them back if you do not have anything in cache. Hopefully and luckily, our CPU founders have spent a lot of time over the past years to add L1 and then L2 and then L3 caches, and then they try to make sure that every core has its own cache, and then every series of cores share a level of cache, and then they have very complex algorithm to make sure that even if you try to read memories that is close to each other, those cache will not interfere with each other too much, to some degree. There are still some limits. But yeah, I think the message is data locality is key, right? If your data is, and by what I mean is if the data you're accessing is next to another data you just accessed, you're good. If not, you have trouble. I'm going to explain it a bit more. So if you, everybody familiar with how caches work? Or should I maybe do some quick recap? Real quick, nice. All right, so, you have caches. It's basically lines because fetching 132 bits or 64-bit word from memory is just not efficient. So every time you try to fetch something from main memory, what your CPU does is actually fetches what we call a cache, a line. It basically finds your address and takes everything that is around 64 bytes around that and just brings it all back to the CPU, to the L1 cache in one go, because it's just more efficient. You can't improve, if you can't improve latency, try to improve throughput, right? That's kind of the idea behind it. So let's say I want to access some variable here. Each of these cells is about 4 bytes. If I try to access this memory cell here because I'm loading an int, I actually get the whole thing fetched for me. Which means that basically if I do this, or if I do this, it keeps getting free because I fetched the thing already. And even better than that, your CPU is not that stupid. If he sees that you're going this one, so he's like, I know what you're doing. You're going there and you're going to continue. So at some point, he's going to just prefetch that one for you before you're even done. And since Intel engineers are actually very smart, we also realize that sometimes you want to go the other way around. It also does it. It's not a problem. Whoever told you go plus plus or minus minus on the loop lied. It's basically the same. CPUs can figure out either way how to prefetch data, which basically means that it's slow, but you can fix that as long as the CPU can predict the access pattern. And he's not very good at predicting the access pattern. He can basically predict plus plus and minus minus in a loop. That's about it. Anything else, you're on your own, buddy. Have fun. So yeah, if you have to take one word out, it's linear access good, random access bad. That's basically the very short summary. Cool. So now that we know that, the plan is, how do we try to design around it? Or to design to work with it? Because again, like you have an interesting speed penalty if you don't take that into account. That's why something called data-oriented design popped up. I didn't want to go the full history yet, but I probably will have to eventually. It's something that popped up maybe 10 or 20 years ago. I think depending on when people started talking about it and using the name as a pattern. But the idea is like architect your code and data structure in a way that benefits your CPU caches. And the more we've gone, the better, the more important it has become. Because again, CPUs are getting faster, but your RAM bus is basically as fast as it was 10 or 15 years ago. They've tried to improve that. You can buy like those fancy RAM sticks that have like a better CL, like latency thing. But it's not gonna change by an order of magnitude. You might get like a 20% speed up or something. So basically the idea is that at the end of the day, what does computer do? It transforms data, right? You take like a bunch of bytes in and then you spit a bunch of bytes out. Well, either that or you're outputting to some device, but that's basically the two things you do. And so CPUs are pretty good at that. And that's where it meets functional programming. When you realize that at the end of the day, if the most efficient thing a CPU is basically doing functional programming to some degree, which is like, it's good at doing functional programming in bulk. So like if you have a math function you want to apply, it's not good if you do it once. But if you have like 1,000 items that you need to apply a math transformation to, it is extremely good. And that's where you get the speed up, and that's where things start going brr. So they have this old debate and idea that you may have heard about called AOS versus SOA, which is array of struct versus structure of array. So let's say I have a very, very like simple game that has units, and my units have like very, very limited amount of property. They have like a position, a velocity, and a bunch of hit points. That's very basic. That's where it is. That's how fast it's moving, and that's how many hit points it has. That's the basic. That's, you know, we've all wrote on that at some point in our life. Or I think most people can see like, yeah, okay, that sounds like the way to represent the thing, right? Because that's what those things kind of make sense together because they form a unit. Your CPU hates that, but it's kind of easy to understand. And the idea with data-oriented is that you would do the opposite. You're like, no, there's no such thing as a unit. Because again, one doesn't matter. The one case doesn't matter. CPUs suck at the one case anyway, so it doesn't really matter how you write it. It's gonna be bad. But they're really good at the many case if you help them. So what you do is you have three vectors. One is all the position, one is all the velocities, and one is all the hit points. I have some nice graph to show you. So that's my unit, right? It's to scale, 32 bits each time. So you have a position, a velocity, and HP. That's what it is in memory. Cool. So if I use a very classic like structure thing, this is how they're gonna look in my memory, right? I have the first unit, then the second unit, the third unit, blah, blah, blah. You see that. Or if you start with 0, the 0, the 1. That's the same idea, right? That's where your fields are in memory. That's where your data is. And then if you start looking at like, okay, what kind of operation will I do with that data? The most obvious thing is like I'm gonna update my position. And I'm really bad at math, especially computer math. But I vaguely understand that the idea of updating a position is you add the velocity to the current position and you get the new position. That's as far as I can go. It's a very simple vector add. Even I can understand it. You can take damage, which basically you have old hit points and you get new hit points. That's just very fancy, simple math function. Arguably, you could have an argument like how much damage you take. That's also a simple math function. And the third one is like rendering, and you're probably going to do something like figuring out if a thing is visible or not. It doesn't output anything in my case, but maybe you output like a bunch of IDs. Like those people are the ones you want to render, and just skip the other ones. Things like that. And I color-coded them for your convenience by which data they each use. And so if you start looking at all those transformations that you kind of assume you're going to do in a loop, right? You're going to do like for each unit, update its position, for each unit, take damage, for each unit, render it. You realize that they don't access the same bits that are all in the same place, right? So let's say I want to update position, okay? So that's what that's the memory I'm gonna fetch, because obviously I'm reading the whole object every time. It's okay. I'm only wasting those bits. Like the HP is the only thing I don't read, so it's acceptable. If I start taking damage, that starts really looking like horrible, because I only read one every 8 cells in memory, and the other one is just garbage data that my function doesn't care. So my for loop and my memory bus are fetching like 8 times what they need to fetch to be able to do this operation. And if I try to render, I mean, it's almost half. It's something. What if I do it the other way around? What if I have a vector of positions, a vector of velocities, and a vector of hit points? So update position, what does it do? It takes the position and the velocity, so it's going to read those two vectors like in a zip view, and this bit is completely ignored. You may argue that unless you have a very good benchmark to prove that it's better, it might not change much. UCPs are usually good enough that you can read 2 arrays in parallel without wasting a lot. Because the way caches work, if like modern caches are like 16-way associative or whatever, which basically is a fancy term to say that you can usually have up to like 16 things that have the same modulo memory thing, and it still works okay. But still, like, I think two arrays in parallel, your CPUs are usually pretty good at it still. Take damage is, well, like orders of magnitude better, because the only thing you're going through is this array of very tightly packed data. So you will get a lot, and render is also good because it only operates on this array. Just doesn't have to care about that memory at all. So again, basically what you're trying to do is say, my contention point is memory fetch and memory push. Try to fetch as little as you can to be able to do the job, because that's your bottleneck. It's kind of the same idea of if you're trying to read things from a disk. If your data is scattered around the disk, you're gonna have to read like your own, like if you ever had to work with CDs, it used to be an optimization people do to improve loading times. They would try to pack the data on the CD because physical drive has to spin and everything like that, and you really don't want to have your data spread around the whole CD if you're trying to load like a texture or something, because that's just gonna take forever. It's the same idea. Just your bottleneck is transport, so minimize the amount you're transporting. So yeah, the idea is like make a bunch of small loops that operates on arrays of fields, and minimize the amount of data in cache that isn't read or write during the update. Don't waste stuff. Don't fetch data you don't need. And even better, I guess, several transforms can run in parallel if the same logical object doesn't share any fields. So if I go back here, for example, take damage only use HP, and update position only use position and velocity, so I can immediately find like a multi-threading opportunity here. Those two data structures are entirely independent. I could run those two on different threads at the same time, and I mean, if you have a modern machine, you can also probably chunk those into several jobs that you could also spin across many cores. But basically, I can multi-thread this for free, or for very cheap. If it was the structure that we had in the first place, it would be way harder, because technically I'm not reading the same fields, but first of all, you have to prove through your code base that those two functions are technically getting non-const access to the same object, but it's fine because they're not reading the same fields, which is already like a scare. Like I would be scared if someone was doing that in my code base, and it's really hard to prove that you're not going to interfere with each other. But on top of that, CPUs really hate when two cores are reading the same data in memory at the same time, because they have to keep the caches consistent, so they keep stopping each other and say, wait, someone changed the bytes. Please throw your cache away and refetch from RAM. I don't have a graph here, but there is a bunch of talks that have been written on the topic. It's called fault sharing. It's when two cores are basically accessing different bytes, but that happens to end up in the same memory like cache line, and that basically tells your CPU to throw away what it has every cycle because somebody else touched it. And just please refresh the page, it has changed. Not good. So to make the point across, I made a very simple benchmark. I could even open it, but that's a lot of code. Maybe there's no point. What time am I on? No, there's no point at that point. What I did is I made like I think it's 10,000 or 100,000 like dummy unit object that have all my free fields, or 9 fields, or 7 fields if you want to count like the X, Y, and Z as separate fields. And then I apply all the free transforms as free for loops. There's no threading. There's nothing. It's just dump. The left one is using arrays of an array of structures, and the other one is update like a structure of array. You're like, that's 20% faster. 1.2. That's a speed up. Is it worth changing my whole code base to get 1.2%? Some people will argue that yes, because they work in finance or something. Some people will like, ship it. It's fine. And I mean, I can understand this argument, right? For some cases, it's fine. Now, obviously, I've worked in several code bases, and your unit type is not going to be just that. Like, I mean, maybe it will be in the first month of your prototype. And then you will start having, I don't know, the model and 20 of a billion field because somebody really needed to add a feature to your application. I'm talking about games here, but you can probably project that in just about anything you need, right? There's going to be a lot of other fields there that are used by many other transforms that none of those care about, but they're there. So we can simulate that, right? We can just add a car here and just put some bytes. See what happens. So let's add 32 bytes padding of nothing. Oh, that starts being a problem. Let's start 64 bytes of padding. Oh. Let's add 120. Oh, God. Yeah. And at some point, it stops. Because basically, you always have to go to main memory every time you're fetching an object because it doesn't even fit in the... one object doesn't fit in the cache anymore. So that's where you start seeing, you can make a graph. And you will... Actually, it's a very interesting way of... if you want to measure how much cache you have on your machine, try different sizes. And you will see the spike when you start being bigger than L1 and then bigger than L2 and then bigger than L3 and then I'm done. Everybody go to main memory. Cool. So what's the point of ECS? Because I've been talking about caches and data-oriented design for 20 minutes now. So ECS stands for Entity Component System. So I guess now that we have showed a bunch of stuff, it might be easier to understand. So the idea is you bundle a bunch of fields that you think make sense together as a component, and unlike a classic struct or class you would do in object-oriented programming, it's just they make sense as in they're part of the same transform. And you give them an ID. You give every object in the world an ID, a unique ID, usually an incremental ID, but some people prefer to name them or just use GUI ID. It doesn't really matter. It's just you need to be able to index them or refer to them. It's a key. And the idea is each entity has an arbitrary number of components. So, for example, my unit has 3 components, right? It's the position, it's the velocity, and it's the HP. But in a pure ECS way, any entity can have just about any arbitrary amount of components that are at any given point active or inactive. And it's supposed to be very efficient at querying all the ones that have a component X. Yeah. That's the idea, right? You can usually add or remove component at runtime. So for example, I don't know, if you have a base unit and then suddenly your unit needs to have some AI data, then you just turn I have an AI component now. And now when I run the AI updates, I will only get the units that actually have an AI and all the other ones will be skipped because they don't have an AI component, so obviously the AI doesn't need to care about them. And then, of course, at the end of the day, the system is just a transform that operates on a selection of components. So you remember the inputs, outputs we have? That's basically the idea. That's a system. And then, for each system update, basically what you do is you gather all the quantity with the entities with all the required components and apply the transform in bulk. So you go through all your tables. If you say okay, I have a system that is updating the position, you go for every entity in the world, find the one that have both a position and a velocity component, and then pass them to my loop in a zip view, basically like a zip of tuples, if you will. So if I want to go back to my system before, so those are my. This is an entity. This is one type of entity that has 3 components. Those are my components, and those are my systems. That's basically the idea behind it. Cool. So in detail. The idea is that a lot of the efficiency comes from breaking down objects because that forces you to break them down into smaller components and storing them in dense arrays. That's the 2 bits, right? First, you break them down to something that is supposed to be very specialized, and then you store them in dense arrays, basically flat packed arrays like we did on our example. That's the gist of it. Which leads to the question, how do we implement that? And that's where we can start looking at some interesting data structures. And am I going too fast? Probably. But you will tell me what my talk is about, and I'll add some slides to one of the parts after this talk. So, what do we want after? What are the constraints we're trying to work with? Because every time you start looking at data structures, it's always a trade-off, right? No data structure is perfect. If we had a data structure that was perfect, we would have stopped thinking about them a long time ago, and this would just be the one. We wouldn't have several includes. You just have one. Use the data structure; it does the thing. But we don't, so let's start looking at our constraints. What is it what we want? What is it that we don't really care about? And then let's see what can work. The obvious thing is we want extremely fast unordered iteration through instances of a given component. So my golden case is give me all the objects that have the property X, and just iterate through all of those, and please make them a span, or the equivalent of a span. I think that is basically a start and a size, a pointer start and a size, or whatever else, like contiguous memory. I might allow you to give me chunks if they're big enough. Like maybe you can do pages or something like that. If your pages are like sufficiently large to be over like minimum cache sizes, you can just say, okay, if maybe you can page them in like 1 megabytes or 10 megabytes. I don't know how big is your cache nowadays. I think L3 is like several megabytes now. So yeah, maybe just say, okay, give me pages of 1 megabyte of components one by one. And that's what I do because that's what my CPU is good at, is a for loop on a vector. So give me that. Yeah, as fast as going through an array is basically the requirement here. If we have tuples, and we will have tuples, because the point is that usually your system does a transform and it takes at least more than just one input output. It may have just one input and one input or one output, or several inputs and one output. You will take more than, it's a function, right? And usually your function takes more than one input, or will take more than one input. So you want you want as fast as you can, maybe not as fast as a single, but you want your zip iteration to be as fast as possible too. That's the second requirement. So like if I make an arbitrary tuple of components, I want to be able to zip iterate through all the entities that have them as fast as I can. I'm willing to discuss how the constraint can be defined. Some systems will say, oh, I want them defined at compile times. Like this is the tuples that will exist in my world. And if you try to create any other one, the system will just say, nope, I'm sorry, this concept does not exist. I will not handle like every possible combination. I will only handle the one you tell me exists. Some other systems will say, okay, I'm fine with that as long as you tell me in advance while I'm running, and then I can do like a prepare to like rearrange maybe the data in memory so it will be fast the next time. Obviously, don't change your mind every frame because that's not going to work. But if you can say, okay, this system will iterate through all those data, you can maybe have the code rearranged, the data structure in behind your back if you need to. With more constraints, we want reasonably fast lookup. Again, the one case is usually not the one we're the most interested about, but we also don't want it to be like a linear search or something like that. Ideally, if you want to look up like all the, if I have a given ID and I say give me the components, like entry number 5, give me its position, you want it to be reasonably fast. Again, we don't optimize for the one case here. That's not the point of data-oriented programming, but there are cases where you want like the classic is UI. You know, you're visualizing one object or debugging. I would say UI. Like you have a UI, you're visualizing one instance of a thing. You want its data and just its data to display to someone. You don't want that to take forever. I think constant time is not always a requirement. You might be able to accept like maybe like a linear, something like a log search. But ideally, you want something close to at least a hash table, if not or if not just a memory pointer jump. And then finally, sometimes we need to iterate through all our components in a deterministic order. So we want to have a somewhat fast way to do that. The reason is, sometimes when you're ordering and updating your system, the order doesn't matter, right? It doesn't matter. You can update them in any order. But sometimes, due to the design of your application, your game in my case, it has to be deterministic. I have to go through every unit by creation order or something like that. It's usually a thing, for example, if you do multiplayer games and both your simulation have to end up with the same result and you have like a data order dependency or something like that. It might happen. So in some cases, you may need that. It's not the biggest thing, but we would like it to be not killing entirely the performance if we have to do it. And finally, our IDs have to be stable upon creation and deletion. So as long as you can look it back up, I'm fine. But if I delete an entity, you don't renumber every other entity in the game. I don't need pointer stability, but I need at least ID stability. That's what I need. That's what the system usually requires to qualify and do the job we want to do here. I've looked at 3 frameworks doing this. Unity Engine, because they made a lot of buzz in 2018 when they announced the Megacity demo and their ECS system. Also, one of the guys who made like a bunch of C++ talk named Mac Acton worked on it for a while. I don't know if he's still there, but he made like a CPPCon talk that is still controversial to this day and at the top of the page because I think it's the most watched about data-oriented programming. I think it's 2014 or 2015. I thought it was very relevant. Even if it's in C#, they have like something behind it. I look at the entity or entity. I think entity is supposed to how you pronounce it. Because it's made by a friend of a colleague on top of that. It's also one of the few open source models actually used in production. Because sadly, ECS is a very vibey topic, which means you will find a lot of engines on the internet that implement an ECS system. And then when you look at users, you find demos and indie games. It's not, I have nothing against them, but you know, my boss is usually more reassured if there's more than one indie company that uses this thing. In the case of Entity, it's using Minecraft. So I don't think Microsoft or Mojang want to run out of money anytime soon, so it's probably working well. Anyone from Mojang on the... Hi! The last one I looked at is Flex, because it has been experimented upon at my company. But I won't talk about it because it's in C, and I don't like C. Sorry, I failed that transition slide, but yeah, I don't respect it, it's in C. It has a C++ binding, but it's on top of the C++, the C API. Also, I was late on those slides, so a better look at less stuff. So, how would we implement a single component case, right? That's the easy way. Let's try to get the easy thing first, and then we can consider the next thing. So the main thing is we can't just use one vector, because we have the ID stability constraint, right? And the only way you do a constant insertion time in a vector is by swapping with the last element when you remove, which is a non-starter because you would change the IDs. So we can't do that, or at least we can't just do that. If you've followed a bunch of papers on SG14 or in the C++ standard, you may have heard about things like colony or hive. The names keep changing as the paper progresses. It's this idea of a data structure that is, it's an array that allows for gaps, and then all the details is about how do you optimize the detection of the gaps for finding the first hole in the thing to make an insert, and when you iterate, how to jump to the next set bit. So usually it's a mix of skip fields and bit fields. It's not a trivial data type to use, but there are some reference implementation on the internet you can find. There are some talks about it. And it could potentially do the thing, because it's supposed to be quite efficient at popping and inserting without breaking IDs. But it comes at the cost of a slightly slower iteration, because, again, it leaves gaps as the thing goes, so you might have to jump. Or, and that's the thing I'm going to explore next, is what if we just, we keep the swap to tail on delete, it's fine. Just make sure that our actual index is not part of the array, right? We allow our component index to not be ordered by very natural ID. Because again, the thing we're trying to optimize is an ordered access. We don't care, like, as long as our index going through the index is not too slow, for the cases where we actually have to have a deterministic iteration, then it's fine to have an external index. Because again, that's not our main case. Lookup is not our main case. We just want insertion to be fast and iteration to be super fast. So yeah, colony has some advantages, but as I said, iteration is slower than vector because you have unused entries, and then also depending on how well you implemented the skip field, you have some logic, you have some cache, you have some branch prediction, because your CPU never knows if the next entry can be read or if he's going to have to jump, and that's a whole topic that I won't even gonna delve into. Also, another problem is like spikes in container size can lead to memory fragmentation. For example, if you have a colony, if you write a lot of stuff and then delete like 2/3 of it, it will still use all the space unless you manage to delete only at the end. So you might have a lot of memory fragmentation if your colony like grows a lot and then goes down, unless you have a manual step that basically does a garbage collection or a full or something, which you can't actually, because again you have the index problem. You will have a lot of fragmentation over time, and you might end up like skipping more than actually iterating through the colony, which is not good. So instead, let's try something else. Let's try to have an external index, and then keep our array like basically packed. We don't have gaps in it. If something has to go, we swap it with the last one in the array, and that's it. So it's always full, and it's always like as packed as it can be. And then we'll figure out how much we're paying for the thing. You will lose the ability to get easily from a component pointer to an ID because that link is broken. You're not guaranteed to have the same ordering. You can restore it by having a third table, but depending on your use case, maybe you don't need to. Like most of the time, the idea is that you come from an entity and you're trying to get its components. It's rarer that you're iterating to one given component and then you say, oh, give me its ID because then I'm going to start fetching something else. Because usually, again, the point of the system is to do zip iteration. It's not the one case. So maybe the one case is okay to be slow. So let's see. So how will we do it? I think one of the names I've called is like the dense array sparse index. I've seen other names around. I should probably list them all in the talk. But the idea is that you have your actual data buffer at the top, which is your arrays, and then you have an index. When you start, as long as you're just inserting, it's basically the arrays are the same, right? The first one is just your data. The second one is just indexes, and they basically match, because the first component is the first byte key, etc., etc. But at some point, you want to start deleting something, and again, we want to keep it sparse, so we're gonna have to swap to tail. So how do we swap to tail? Well, first we mark that now it's -1, which means like this entry is not used anymore, and then we just flip it with the last one. And did I fill something here? Yeah, no. And then we update. Did I? Yep. And then we had an entry for that one, saying that this one is now here. I'm pretty sure that slide is wrong. No, I think it's correct. Yeah, that one is now here. So that's fine. We're okay. We can find it. I'm pretty sure that slide is wrong. I need to fix it. I apologize if that's not clear. Are you following me so far? Because I see some very confused faces. So, okay. So I think that slide is incorrect. But the base ID is like every time if you want to look up something by its ID, you jump on the ID on the table and it will tell you which slot it is supposed to occupy. So what I should have done instead of that weird thing I've just did is that I should not have popped that number. I should have replaced it with 1 because that's actually what we did, right? We killed that entry, so we move 6 here, and then the last entry instead of being removed should have been a 1 because you're basically pointing to entry number 1. I will remember to fix this slide later. Yeah, okay, that's what I done. I've just done it really ugly. I should not have removed that one. So now, if I'm looking for entity 6, I know that I have to go to this memory cell instead of this memory cell. So now I'm not in order anymore up there, but I'm still compact, and that's what I want. There is obviously an indirection cost, right? Every time you do a lookup by index, you have to do a first memory jump followed by a second memory jump. So it's a pointer indirection, basically. It's the cost you have to pay to get there. Again, it's not our main use case. If you keep banging on this, you're not doing what the system is supposed to be used for. And then if later I want to insert a new item, like entry number 7, I'll put it at the end, and then I'll just add a new entry saying that it's here now. Again, one more slide probably needed to explain this. And then if I really want to do a reverse index, I can have a third array that is always the same as the active component that just tell me where it is. And so if I have a pointer to a component and I want to know which actual ID it is, I can do like a pointer diff to figure out what's its offset here, and then from the offset I can check this table and see where that is. The reason I'm doing this is because I don't want to store the ID in the component, because again, most of the time when the component is updating, it doesn't need to know about its own ID, because again, going back to IDs is trying to chase individual items, and that's not the thing we're trying to do here. The main ID is always the same. Every time I need to access something that is not the main job, it has to be another table. That's a bit confusing at first when you start using this, because for example, you usually use that if you have like if someone passes you a pointer to an object, you can do .getID on it. On this one, you can't. You have to go back to the table and say, please look up the ID of this item and tell me what it is. I guess it gives you a code smell, because it tells you like, why are you doing this all the time? You shouldn't be doing this unless you're doing maybe like not a bulk operation, like again, like UI or one-time thing. Like if the user clicks on one button and needs to affect one entity in the game, then it's fine. You can actually go and say, give me that entity and change whatever the player did. That's okay, because the player is one person, but what we're simulating is everything else. So the idea is that it's as easy as 2 or 3 arrays. You can implement it in a couple hours. It's really not that hard. I've done it, and there are you can find reference implementations on the internet. You can start splitting the second array into pages if fragmentation becomes an issue. Because again, second array is as big as your highest index. So if you start having a lot of holes in your indexes, you will start having a very large array full of -1s everywhere. So you might want to start it using like an indirection page system to avoid gaps. But you can also solve it in another way. I'll explain that later. You could use a hash table, except if you use a hash table, you don't solve the problem of ordered iteration. You solve the problem of lookup in constant time, and usually hash tables are better at memory efficiency than open indexes. But hash tables are unordered, so you go back to the problem that it's impossible to iterate through the components in a deterministic order. Unless you do a forward 0 to whatever, just do a lookup. You could do that. Not sure it's that efficient, but that's technically an option, I suppose. Never tried it. A thing also that we figured out in game industry usually, and hopefully in other disciplines too, but if you don't, well, that's a freebie for you. Incremental IDs are bad if you only use incremental IDs, because eventually you will have lots of dead objects in your index sequence, because things come and go all the time. Especially in games, like if an ID is a unit or a monster, they keep spawning and dying all the time. It's really a waste if it keeps incrementing. We are wasting a lot there. So instead, what we do is usually we split the ID into 2 bits. We have a physical index, which is basically what you would assume is an ID, and then we have a generation ID, which starts at 0. And what it does is that it allows you to do an ID reuse. So like if entity number 1 dies eventually, what you can do is say, okay, this is entity 1.2 now. It's not the same one. It technically, like the system can realize that if you still have a request to dereference it can tell that this is a different object. So your lookups will still tell you that this is not found. But it basically allows you to reuse the memory cells and try to reinsert at the beginning of the index sequence if you can. I have an example to explain. So this is our index right now, right? Okay, I have 0, 1, 2, 3, 4, 5. Well, it's not really like this is our mapping of indices, right? So okay, so instead of that, let's give them a version number, right? So instead of being 1, 2, 3, 4, 5, blah, 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 it's okay. It's version 1. This one is not used, so it's -1. Version 1, version 1, version 1, version 1. So if someone tries to access entity number 1, which is here, you'll look at it and say, wait, it's a -1, so it's dead. But if we decide to reuse it later, so we do an insertion and we say, okay, someone needs a new free ID, and we realize that that one is empty, you can give it and put it there. I realize that those styles are absolutely impossible to understand. Okay, I will need to rework this. My point is, instead of incrementing my IDs at the end, yeah, do I have another slide? No, I don't have another slide. Damn, I'm sorry. This is the pain of doing slides like 5 minutes before 2 releases. The point is, your IDs, instead of creating, like I could have created an ID 7, but if you look physically, I'm not, right? I'm still here, I'm in this slot. And the idea behind it is that since my index has 2 parts, I can reuse an older gap in the index sequence and just increment like a fraction number under it. Like, see it like versioning, like, I'm looking for a version, like when I create the object for the first time here, it will be it will be object like 1.0. And then if I destroy it and create another one, technically his name will be 1.1. As far as indexes go, they fall in the same memory cell. But when I do a lookup, 1.1 and 1.0 are not the same thing, so my lookup will return that it's not found because I'm looking for something that is dead now. It's basically a way to hide the memory explosion of creating and deleting a lot of things and trying to reuse all the indices when possible. And this is mostly done so that your index table doesn't grow to like 4 billions or however memory you can have. I will try to explain that way better in the read-on presentation because I'm sure I'm confusing everybody right here. And now I'm going to talk about something even more complex, maybe. So, how do we iterate through multiple components? Because the first case is somewhat easy, right? We have an array, we keep it like basically in an undetermined order. We make sure that we always swap to tail or with tail all the time. That's guaranteed, that's fine. But it starts being a problem when we start trying to iterate through two elements. For example, if we go back to our case when we have a vector of position and a vector of velocities. As long as I only have objects that have both components, those two arrays will be in sync, right? Because when I will pop from one, I will pop from the other. When I insert in one, I will insert to the other. But again, you can have combination. You can have a system, for example, that only cares about positions, and maybe some components are optional. We talked about AI, for example. If you assume that every unit has a position, a component, a position, a velocity, and maybe an AI, then my tables will obviously have different sizes because maybe like one in third components have actually 1/3 of the entities actually have an AI component, and all the others don't. So my arrays cannot be in sync by construction if they don't have the same size. And now becomes the problem. How do I do an iteration through a zip view? Because ideally I would have these two arrays sorted the same way. And since they're sorted the same way, I can just do a zip view and go through them one by one. But I'm not guaranteed to do that. So how can I solve it? There are several ways to do that. A common one is called Archetypes, in which you pre-declare the kinds of tuples you will have in your system, either at compile time or at runtime. And basically, it will try to lay out the data structures by creating constraints. So for example, if you say, oh, I have an archetype that has a position and a velocity, then you basically tell the system those two tables should always be in sync in terms of internal ordering. And that way, if you want to iterate through both of them at the same time, it's just a zip view and you're done. Obviously, that's not always possible, potentially because, as I explained, you start having optional components and that breaks the rule. And in which case, for example, in the case of Unity, you can create archetypes on the fly. And what they will do is they will try to create dedicated component tables with all the fields you actually need. So instead of having like 3 components, for example, if I say I have an archetype in my game that is position, velocity, and AI, it will basically create a table which contains like tuples of those 3 components, and you will iterate through all those components when you iterate through it. And if you only ask for 2 of them, you will get some overhead because you will have the AI component that will be skipped in memory. But it will try to still keep it efficient as long as you don't have like every possible combination of tuples. The drawback is every time you add or remove components to entities, they might change archetypes, and if they change archetypes, they change physical location, which means a lot of memcopy. I'm told it's one of the things that tricks people when they start using the system with Unity, is they keep adding and removing components all the time, and they don't even do it in bulk, and you keep having memory rearrangement all the time behind the scenes because the system is desperately trying to keep all your table nightly packed in memory for fast iteration. Like I said, it doesn't scale well if you have many archetypes that share some but not all the components, because at some point it runs out of options. It's like, there's just all those possible permutation of two given components exist in my thing. There is no one true order I can have because depending on your use case, you're gonna want any 2 of those, and there's no way I can have I can only order them once, and then everybody else has to pay for something. ENTT goes different. It basically doesn't do anything. You can have archetypes, it doesn't really care about it. The only thing it does is that it assumes smartly that the fastest iteration is gonna be to go through the smallest component. So like if you ask for AI, position, and velocity, for example, it will say, hey, the smallest of those 3 tables is AI, because obviously you only have one in 3 objects compared to the other 3. So I will linearly iterate through that table, and then to give you the other 2, I will do lookups. You will pay for a lookup, so you will have an indirection for the other components. It's clearly not as fast, but on the other hand, especially if your components are unbalanced in size, like for example, if you have a lot of position but very few AIs, you're not gonna pay for that many lookups, and that's how it tries to alleviate the problem. It's not perfect, but since it's just a jump, the hope is that it still manages to avoid the biggest caveats. Do I explain that correctly? Yes. So for example, if I'm iterating through component 1 and 2, I'm going to try to start, okay, for component 1, I'm going to try to look up its index in the second table. Well, second table doesn't have that component, so I can skip it. Okay, number 5, I have it in both, so okay, I have to do a memory jump here, a memory jump here, and then here's your first tuple. You can do your iteration with that element. Then the number 2, well, it's easy, it's there, so every time it's a pointer jump. So that's 2 fetches every time, and as you can see, they're not guaranteed to be collocated. If your array starts being very big and your components have literally nothing in common in the way they're internally ordered, you will still be jumping to memory all the time. That's not ideal, but the hope is that they still share some commonalities. And if not, I think some systems have considered having like a temporary sort, basically, which is kind of the same as what Unity could do. Say, okay, this is the one I care about, so make sure that those two are always sorted the same way. You could potentially do better, as I said, if at compile time you know which pairs or which tuples will actually be used, or at least are the ones that you really care about. You can say, okay, those 2 tables should always share the same internal ordering. And that way I can just do zip views, and that's basically as fast as anything can go. And for everything else, well, I will have to do a jump. I'll pay for it, because that's life. There is no easy way to solve it as soon as you start sharing components across system. So this is the magic, this is the promise, this is the ECS that everybody says I should solve all my problems. Did it solve any of my problems? Let's see. So how do we use, so I took a very practical case, which is the games I make, because that's what I know. We don't use it. Well, that's it. I should go home. Okay, that's not entirely true. We don't use it in production. We are looking at possible uses in the future, because as the industry goes, we are usually late on tech. That includes compiler, but also includes this. We are looking at it for engine and rendering, because that's usually a lot of where it's used, because it's usually very small table and not very focused. So like everything, so like render paths that have to go through a lot of items and say, okay, select the one I care about. When you have to transform lots of very small operations that are done on engine level that are usually tied to rendering are usually a good candidate. So we started looking into this. Now the next question is, I make very big simulation and my game is not bound by rendering, it's bound by simulation and the gameplay. Can I use it on the gameplay? Well, from what I've started trying to experiment with, it works better with small components and disjoint archetypes, because basically they can be kept in their own separate realms of tiny tables that are ordered the same way. As soon as they start sharing components, then at least one of the 2 components in the iteration will have to pay the lookup price for every item, and then you start losing the benefits of having the whole system. And for some reason, a lot of ECSs will always say, you know what, by default, every entity you create lives in the world. Don't worry about it. It's a one global selection of indexes, and any item in this world can have any component. This is bad. This is bad because it doesn't give constraints, and the way you get fast in computer science is by determining construct that allows you to cut corners. And for example, if I know that two components can never be in the same realm, then I know that I don't have to care about them having the same index sequence. They can use different IDs and stuff like that. It starts becoming a pain when at first you design something and say it's fine, those two concepts will never ever share a component. And then the designer comes and taps you on the shoulder like, would it be great if a province could also be a building? And I'm like, but those are 2 different containers and they have different indices. And if I start merging them, then I have to start merging every other component there, and then you end up with a bucket. That's not great. But in my experience also, most archetypes can be defined at compile time. It's really, really rare that you start creating new combinations of components that you never thought could exist. Usually, they exist and you could give them a name, because that's the point of the update, right? For example, a thing that has a position, a velocity, and hit points is a unit. That's the only thing in the game that has that, and I can tell. And I'm not gonna start making arbitrary composition that make no logical sense in my in the headspace of my design. Like I said, the problem with ECS is that when you work on our games, which design philosophy is, we have a lot of systems. They're kind of boring separately, but the thing is they all interact with each other in weird ways. So they really, really, really don't like you when they come and say, wait, I have this system, can I just like chug input from like 3 other systems, 3 other components out of the blue? You're like, not really. And they're like, oh, because in the previous engine I could. It was great. What do I do? So what I suggested and what we're trying to do is like, okay, define some updates as 3 functions. So it's basically go back to functional programming and the idea that an update is just a thing that takes an item or a span of items and outputs a span of item. Oh. Then you try to constrain the inputs by type, and by type I mean type of components, and the smallest the better. So for example, there's always a question like, should position and velocity be one thing because they always hack together, or should they be 2 different tables? Question is, do you always use them in tandem, or as soon as you start using them together, you should split them, if you can. Which again makes any design change potentially way more dangerous and complex because you suddenly have to split classes. Yeah, and once you have those 2, start considering, okay, you know what? I have those 2 things. I have my own like databases or storage vectors, arrays. Maybe I could try to consider some ECS storage system instead. I could kind of call this talk like I used this system and it didn't solve any of my problems, but that's not entirely true. So there seems some value to take out of there because I know I put a lot of caveats on the list. Well, first of all, is that you can't deny that data-oriented approach yields important speed-ups, and especially nowadays, and it's just not gonna get any better. I don't see any reason why it's gonna get any better. I don't work at Intel, right? So maybe they'll prove me wrong and invent like a mega cache like built by the dwarf of Moria or something, and it can solve all your problems, and it basically restores like the balance between memory fetch and CPU instructions. I just don't think physics agree, but I suck at physics, so don't take my word for it. Having multiple components ECS implementation is tricky, and I haven't found a lot of good uses for it, or it's difficult to use. But what I found use for is just the concept of like simple data structures that are reusable, and the main one has been the dense sparse array. I have found like bespoke systems in my game that used to just have like a huge map or hash map or whatever of objects, and instead I just say, nope, I'm gonna put all of them in a completely unordered array that just swap to tail every time I remove an element, and I'm gonna have an external index. That's just a simple pattern, but then when you realize that what the most thing you do is just iterate through all the objects and apply a transform to them in some form, you can immediately start doing stuff that is, well, way faster. Because again, this is a really nice data structure. And I guess this is maybe what my talk is about, but again, you tell me at the end. I have some questions. I should have put like a slide with questions. It's the fastest you can get for an ordered iteration, but I mean, it's as fast as vector, so that's not really hard. It's constant insertion and deletion with constant lookup by ID, with ID stability, not pointer stability, again, because you can move items, but as long as you have a constant lookup time, it's probably acceptable. And it's okay, but not amazing deterministic iteration speed. Obviously, avoid it with non-trivially relocatable types, because you may end up. It relies a lot of memcopy basically behind the scenes to keep things nice, and it does a bunch of moves left and right. So you may want something better for that purpose. Cool. I reached the end of my talk. I hope it made sense, because again, circumstances. But in conclusion, so memory access is really easily one of the biggest performance bottlenecks you can find today. And I didn't insist on that. It's really hard to measure. Because, I mean, you can chug your program into something very complex like vtune or perf or basically a micro profiler of sorts that actually look at the cycles of your instruction. But that's not what the average profiler does, right? The average profiler tells you this function is slow. And it might be hard to see at first glance that your problem, especially on a big application, that your problem is memory latency because it's hidden behind something that looks way more complex than it is. And yeah, I have to bash OOP there because, I mean, it's not, OOP has its advantages, but it's really bad at this because it makes you have pointers everywhere and lots of fields that have nothing to do with each other. Well, they conceptually have something to do with each other, but they don't have a lot to do with each other as far as an actual heavy bulk computation is involved. Consider structures of arrays of structures. That's the same idea. If you can really tightly pack your data, you are gonna get a better bang for buck from your memory bus. And ECS may be overkill, especially because for some reason the game industry really likes frameworks and very heavy things. They don't like libraries for some reason. I've tried to look for an engine, for example, recently, and it's like, no, you have an engine. You don't have like an API. It takes control of your program and determines how your programs run now, and I don't like that. But it's an option, and if not, just look at the dense parse array pattern. I think it's a really interesting and cool pattern. It's been giving me some interesting results. And furthermore, I still think your build should be destroyed because I need to find something else to tell. Question, remarks, tomatoes, feel free. Just for reference, the guy who makes Entity, his name is Michele Caini. My Italian is really bad. Michele, if you're watching. He has a really good blog where he made a series called ECS Back and Forth where he explains entirely how he implemented Entity and, for example, the data pattern he uses for single and multiple iterations. All that stuff is very neatly explained there. I think he has a talk version of it in an Italian C++ conference somewhere. And you can also check the project, because I think if you want to go for something free, it's probably the most solid option. And with that, we can go back to questions. What?
That this was a rehearsal for the CPP.
Yes, I will be giving a full version of another revised version of this talk at Meeting C++ in Berlin. So my question to you is, what is my talk about? Because I'm not sure actually. I changed my mind several times as I was writing it. I'm probably sure I should figure out what it is and just cut a bit of the rest. So I'm willing to take suggestions or questions. Yes.
Engineering trade-offs.
Yeah, I guess if I had a keynote. Yes. Yes. We are trying to use Flex for rendering. That's a choice that was made for reasons that I...
That was the first part of my question. My question was, how many objects do you use before you find... I mean, do you have a million?
I have some people that could be better suited to answer that question in the room, maybe?
Come again?
Paradox engine programmers, I see you there. They're all trying to look behind them. Like, I don't know, man, I'll just work here. I think it's million-ish. I think that sounds about right.
We're talking millions of objects before this gets useful.
Probably you can go less. Again, depends what you're doing and how much you want to pay for it. I think, honestly, it doesn't have to be millions. My dumb test case was like 100,000, and it was a very simple object. It really, and I didn't try to do the full OOP thing because the full OOP thing would have been an array of pointers. Because a lot of storage in my games today is not even arrays of objects, it's arrays of pointers. They're not even guaranteed to be collocated at all. And I can tell you that in some cases, you pay a lot for it. Pathfinding is one of the big cases. Because every time I try to go to the next province on the map to try to evaluate if it's getting me closer to my place, I basically pay for at least a couple memory lookups. Because it's nowhere near cache.
My second question, do you, like for a game, for example, maybe you don't want to update all the objects, maybe just like the objects you see or the objects you is around you in a boundary of maybe 100 meters or 1 kilometer or something. Have you used it like that?
You can, as
when you have a spatial...
well, if you have a spatial thing, That's an interesting question. I think if they explain it in the Mega City talk that Unity did to explain how they did it, they did by doing some data hierarchy basically, and making sure that things were already kind of pre-ordered there. So I don't think they used an ECS per se, because again, if you have a very specific case, maybe you just want to take the lessons of how you would do it, but then do a custom storage. And then they do cells or the equivalent of cells. I don't think, I think in the talk he says that he didn't even have to think about oct trees or quad trees or things like that, because as it turns out, a lot of the things he was already doing was already kind of sorted by the way the game was representing the world. It was easy to say, give me all the buildings in this area.
Yeah, but what if it's cars? I mean, they move around, right?
Yes, no, I think the case of the mega city was you're flying through a city that is always static. If they keep moving, well, there's two options, right, that I can think about. The first one is you have to add and remove them to an oct tree or another kind of spatial representation all the time. As has been shown, I think, by one of the talk of Björn, sometimes doing the dumb thing is faster. So sometimes, instead of trying to like add and insert stuff in like a binary tree or something, just chug through all those objects as fast as you can and just get all the ones that pass the test. Because if you have 100,000 objects, and just a bunch of like, each one has like a vector free for its position, and you can do like a very simple math to tell you if it's visible or not. Maybe the simple thing to do is just chug through all of those and say, give me all the IDs that match. It depends. It's a thing that's getting seen more and more, I think, based on data locality, is that linear search is starting to beat binary search. In cases that are starting to get slightly big, because of a mix of jumping and branch conditions, or branch misprediction. So sometimes doing the dumb thing is faster.
I have one question.
Yes.
You have your previous experience before you. How did you come in touch with this?
What?
How did you come in touch with entity?
Uh,
You have your previous experience. What did this improve in your performance?
So again, I've mostly explored the topic more than used it, and then I took some lessons of what's the implementation behind it trying to do and why it's doing it, to try to improve my own data structure. I guess that could be the title of my talk, is how I looked at an ECS and figured out what bits I wanted to use for my own data structures. Because again, a lot of existing code doesn't like to be fed an entire system that says, give me literally every object you have. And please rewrite them in this way, because that's very costly. On a new project, it's a bit more of a question. I have been looking at talks that mention people using them entirely. I don't have first-hand experience in using it at large scale. I mostly took the lessons of like the way some of the philosophy behind it and the data is organized to basically kind of pimp my own data structures. Yes.
Have you considered concurrency, how to, if an ECS could be used to
Yes.
do concurrency?
Yes, and it's usually pretty good at it, because if you want to concurrently, concurrency has two, the way you do concurrency is, one, you need to have everything iterable, if possible, in some form of random access, because what you're going to do is take your collection and chunk it. Arrays are really good at being chunked, lists are really bad at being chunked, right?
Well, that's not what I meant. What I meant was that different system can declare what type of data they
Yes.
need to write, and then you can
So there's two things. There is
what to run.
there is intra-system concurrency, which is what Unity does, for example. Unity assumes that since everything is packed in an array and all your transforms are supposed to be unordered by definition, not order dependent, then you can chunk your system and then throw the computation across threads. That's intra-system computation. And then the other one I mentioned earlier is like, if you find that two different systems do not share any input or output, then you can run them at the same time. That's the bit where actually I have the revised version of my talk about threading in Paradox games actually mentions that we have started experimenting with that on secret stuff, where we try to declare what our inputs and outputs are. We have not worked on the data storage yet. That was one of the reasons why I started looking into this. But we have looked at the make a job scheduler that is basically look at those inputs, look at those outputs, schedule those jobs, because I can prove that those two things are not using the same data.